Hello everyone, welcome to this SCIT conference research paper presentation on the topic Numerical Modeling of Pressure Surges and their Effect on the Integrity of a Water Transmission Pipeline System. The authors are Udochukwu, Kevwe, Ejenakevwe, Godwin, Unachukwu, Samuel, Enibe, Chibeoso, Wodi, Chibuzo, Ikwuagwu. The presenter is Udochukwu, Anuta. Introduction. The study of pressure rise during hydraulic transients is essential to maintain system integrity. This hydraulic transient is associated with water hammer. What is this water hammer? Water hammer is a disastrous pressure surge phenomenon developed during transient pressure conditions inside a water transmission pipeline. These water hammer conditions are also caused by sudden change in flow condition within a water transmission pipeline. These transient pressure conditions are triggered by critical conditions such as pump trips or power failure to pumps. These pump trips or power failure to pumps introduces high pressure fluctuation inside the water transmission pipeline that can lead to pipeline failure or instant pipeline damage if the pressure introduced by these fluctuations exceeds the pressure range stipulated by the manufacturer. For us to understand this transient nature of this water hammer phenomenon, it is important for us to employ computer modeling and flow analysis techniques such as computational fluid dynamics for us to capture this fast fluid behavior and interaction with pipe walls. What is this computational fluid dynamics, CFD? It's a science that simulates flow phenomena by solving fluid dynamics equations such as mass and momentum conservation equations using numerical methods. CFD codes such as ANSYS Fluent and COMSOL Multiphysics present a comprehensive modeling capabilities that can model different types of flow, ranging from simple geometries to complex geometries. Background of the study. The case study, which is Ajalli water supply scheme, experiencing power failure resulting to sudden shutdown of pump, introducing pressure transient that is linked to water hammer. For us to understand this water hammer very well, we also have to define water hammer in a different way as a surge or pressure wave that is created due to sudden change in flow velocity in a confined system. The name water hammer originates from hammering sound that sometimes accompanies this phenomenon. It is important for us to note here that this water hammer phenomenon is very important consideration during design of many hydraulic structures due to extreme variations in pressure it causes. We also have to know that for us to analyze this water hammer phenomenon, mathematical method is employed. This mathematical method analyzes water hammer by solving velocity and pressure equation for well-defined elevation profile of the system, given certain initial and boundary condition of the system. The goal is to mainly solve the unknown velocity and pressure for independent variables of position and time. We also have to note here that the equation can be modified to solve for flow rate denoted by Q and the head denoted by H. The problem statement. The residents and industries within this supply scheme are largely dependent on this Ajalli water scheme, which is a very gigantic water scheme. We also have to know that this water hammer is extremely dangerous and leads to failure of pipeline integrity because of excess pressure it induces. We also have to note again that the study of this water hammer phenomenon in hydraulic system is very important due to safety, economy of plant, and poor performance. We also have to know that consequently, because of this problem of pipeline integrity caused by transient water hammer phenomenon, water consumers within this supply scheme are faced with severe scarcity, which present them to costly water supply alternative as temporary solutions to their plight. Aim and objective. The aim of this research is to study these pressure surges and their effect to ascertain possible solution to this pipeline integrity problem. In order to achieve this aim, the following objectives are carried out: to study the configuration of the system, to ascertain the nature and cause of this hydraulic transient, to model the transient flow of the system using CFD software, also to predict maximum pressure in the system, and also determine flow parameter variation in the pipeline with respect to time during pump trip. Significance and scope of this study. The significance of the study is to provide possible solution to this pipeline integrity problems, also to provide insight into fluid flow and interaction with pipeline wall in order to understand better these transient events inducing high pressures, also to provide a guide to analyze pressure surges using CFD software in system conveying water through pipelines and susceptible to pressure transient phenomena. You also have to note here that this water scheme represents a large economic investment. So its smooth operations and safety must be guaranteed. The scope of this study, this work is limited to CFD modeling of the system. For us to understand hydraulic transient in water pipes, two important theories are put forward where the basis of different mathematical models are developed. One is a rigid column theory. This neglects the compressibility of fluid and elasticity of the pipe wall in analyzing the flow situation. Why elastic theory, considers the compressibility of the fluid and the elasticity of the pipe walls in analyzing the flow situation. There are different hydraulic transient models obtainable. One is one-dimensional hydraulic transient model. One is wall shear stress models. The third one is two-dimensional hydraulic transient model, while the fourth one is turbulent models. So the turbulent model is also important to capture the turbulent nature of this transient water hammer phenomenon, because it tends to accommodate both the mean and fluctuating term experienced during this transient water hammer phenomenon. Methods of analysis of this hydraulic transient: we have graphical method, we have method of characteristic, we have implicit method, we have the wave plan analysis method, we have computational fluid dynamics modeling. The most popular of this method for one-dimensional water hammer analysis, excluding computational fluid dynamics modeling, which tend to model the three-dimensional flow of water hammer phenomenon, is a method of characteristic. It's usually one-dimensional and uses finite different numerical method to solve two partial differential equations developed from momentum and mass conservation equation in order to determine the flow rate and the head in transmission pipeline system. In order to model a system using computational fluid dynamics, three important steps are followed. One is defining the mathematical model. Two is discretization of problem domain. Then the third one is CFD modeling of turbulence. In CFD analysis of pipeline, there are 5 technical processes that must be followed. One is preliminary study phase. Two is the geometrical modeling, where you design the geometry of the system. One is meshing, where you define the geometry of the system into divisions and surfaces for the application of the applicable equation and solving afterward. Then solver setup for simulation, where you set up some conditions that will enable you to analyze the flow problem. Then data visualization and post-processing, just an interface for the user to see the result of the simulation. Then justification for the study: we have that the existing water hammer analysis is one dimension, which method of characteristics is a method to analyze it. So it's limited to one-dimensional classical method of analysis, which cannot fully characterize the transient flow. Then the one-dimensional method of MOC of analysis uses rectangular and diamond grids, which do not accommodate the pipe length and also the geometrical shape of the of the pipeline for purpose of analysis. We also have to know that CFD produce accurate results using advanced machine tools and has the capability to model complex geometry. We also look for that the knowledge gained here will be helpful in preventing, mitigating, and accommodating water hammer existing in this case study Ajalli water scheme transmission pipeline system. This is the 3D front view of the system for analysis with very important features like salt chamber, bypass valve. We also have the transmission pipeline. We also have the conventional check valve. We also have the 3D model description of the system in all views with the table of material indicating each component of the system. We also have equation describing water hammer phenomenon. One of the equations that describe the water hammer equation is classical water hammer transient equation, which are developed from continuous and momentum equation given by equation 3.18 and 3.19. These two equations are used to solve the unknowns such as the head and the head, which is denoted by H, and the flow rate, which is denoted by Q, as well as the second equation can be used to solve for the friction factor and the diameter of the pipe as well. We also have in modeling CFD modeling, have two important equations developed from continuity and momentum equation. These two equations are general form of this governing equation for CFD modeling. The momentum equation denoted by 3.21 is modified into popular Navier-Stokes equation by introducing Cauchy stress tensor, which describes the state of a stress inside a deformable body. We also have CFD modeling of turbulence, where the Navier-Stokes equation is also modified into time average Navier-Stokes equation by introducing Reynolds stress tensor that can be used to model the mean and fluctuating terms of turbulence. In CFD modeling, we also have the important code for the analysis, which is based on ANSYS Fluent R 19.2 academic and COMSOL Multiphysics version 5.3 CFD code. These two codes present a high modeling comprehensive modeling capability that can model different flow types and also different geometries. CFD modeling input, the parameters and conditions are given as initial condition. At time 0, we have the initial velocity to be 0. We also have the inlet pressure to be 22 bar, and we also have velocity to be 7 meters per second. We have the wall condition to be on no slip condition, which we assume that the pipe walls are considered to be hydraulically smooth. We also have the outlet pressure at 1 bar, which is the atmospheric pressure. We also have the time step recommended in the literature to give accurate result at 0.01 second. Also have the time interval of 5 seconds. This is CFD modeling setup, where you define the geometry, you generate your mesh, pre-processing as well, and model the verification. When you set up the simulation and model verification, if it converges, you go further to post-processing the solution and the result. When it doesn't converge, you go back to pre-processing, where you adjust your conditions in order to assume a new computation that can lead to convergence of the solution. This is the mesh geometry of the system, where you have the mesh consists of 1,220,972 domain elements, where you have the boundary element to be 52,504. You also have the edge element to be 1,465. This is the results and discussions. On steady pressure variation with time result, we can see that the maximum pressure experienced after 5 seconds, 5-second interval is 22.51 bar, and the location of this high pressure impact is on the pipe wall, given by the contour line denoted by the red lines. And you also see that the point of attachment of this salt chamber also experiencing this highest peak pressure of 22.41 bars. After 10 to 30 seconds, you can see that the contour lines start attenuating, showing that the system is gradually reducing in the intensity until it attained a steady state condition at 30 seconds interval. So we also look at the transient pressure fluctuation along the pipe over 30 seconds. You can see that the graphical representation show that after 5 seconds, you have the peak pressure at to 2.41 bar, which gradually reduces until the system attains zero pressure at 30 seconds. We also look at the pressure contour plot showing the point of high pressure, where you see that the point of attachment of the salt chamber joints like connection of conventional check valve and some other joint experience the highest pressure load on the system. We conclude from here that given the result of the analysis, that the hydraulic transient induce high pressure in the system, and the maximum pressure experience is 22.41 bar recorded, fall below the pipe design pressure of 41.5 bar. This is owing to the presence of salt chamber within the system, which could mean that places of high pressure effect could be as a result of obstruction in the system. Also know that the 3D transient model shows that the pump trip due to power failure generate pressure surge that travel downstream the pipeline and up to the salt chamber, resulting in water harm on the pipe wall. Also notice that because of this obstruction, the pressure load at the point of attachment and joint location is accompanied by vortex shedding, which enhance the transient flow around those joints within the system as the fluid flow experiences opposition during the hydraulic transient. We also have to know that though the long computation time is also limiting factor in applying CFD for transient analysis in pressurized pipelines, CFD remains a great tool for improving the accuracy of 1D, 2D models and understanding the dynamics of transient phenomena. These are the references. Thank you for listening.